Well, hello. Our topic today is called slope fields. So this is kind of crazy for us today. We're going to be looking at a lot of different graphical representations of differential equations today. So what is a slope field? Well, like I just said, it's a graphical representation of the general solution to a differential equation. So basically, it's a field of slopes, just like the name, slope field. It's a field of slopes. So just to point out, when we solved those differential equations the past couple days, and we did what we called separation of variables, basically, that's called an analytic approach. All right, or we're solving using algebra. Today, we're going to solve differential equations through a graphical approach called a slope field, which again is just graphical. So we're going to look at a lot of wild and crazy pictures, similar that look, to one that looks like this, and we'll take them apart and see how they go. All right, so I do want you to copy this in your notebook here. A general solution has an infinite amount of solutions, which means that it has a plus c on it, that are parallel to each other. Okay, now, you may not be thinking parallel in the sense that two lines that look like this are parallel and they never touch. Well, these are going to be two functions, for example. So if I said, here's one function, if I wanted to make a parallel function, again, I would kind of draw one maybe below it or above it, and the idea is that these functions are still never going to touch. They are parallel to each other. And again, this slope field that we draw is going to give us the visual image of this general solution. So I just want to point out, when we graph these slope fields, there are an infinite amount of answers. Okay, infinite amount of answers. All right, we're going to start with a very friendly example where we're just going to practice sketching a particular solution. So this is something, a very, very, very common question on the AP, where they give you a slope field, and they just want you to graph one particular solution. So let's say, for example, they told us to graph the particular solution, and we'll say it went through the point 0, -2. Okay, so the first thing I would do is, of course, plot that point 0, -2, and that would fall right here. And now, my goal is to draw in the solution just following the breadcrumbs, so to speak, or following the slopes here. To the right of this point, I think you would agree that these slopes are headed down this way. So I'm going to extend my line this way with a nice arrow on the end. And if I were to come in from the left and follow, it looks like they're going up, but then they kind of curve back down. You're just kind of following, almost like a lane while you're driving. Okay, it looks like it's going up, and you're just following the arrows, and they're kind of going back down. Okay, so one important thing to notice is that I haven't used my entire graph, so to speak. I went from this edge of the graph paper, and I went to this edge. And if you don't go all the way, that's a very common point they're going to ding you on. So just make sure you go from end to end. So again, there's an infinite amount of solutions here, okay? But there's only one particular solution that goes through this point. Let's draw another point. Let's say they gave us the point -1, -0.5. And I'm just going to switch colors here so it looks a little more obvious. So again, I'm just going to start by plotting that point. -1, -0.5 looks about there. I'm going to follow again the breadcrumbs, or the flow of traffic, if you will. So it looks like, if I were to go to the right of this point, it looks like they're going to go up a little, and then they all kind of head downwards. So I'm going to go up and down, and again, arrow on the end. And if I were to go to the left, it looks like they're all kind of squeezing in here. And again, I'm just going to go to the end of the paper with a nice arrow on the end. Now, I just want to be clear that these two functions will never cross each other. Okay, so remember we said they're all kind of parallel solutions to each other, so to speak, parallel in the sense that they're not going to intersect each other. Now, you'll notice something else I was kind of wary of. To me, this looks like a straight line here, kind of like an asymptote or asymptotic behavior. So I just want to be clear, I did not touch that as well. Let's try another example. Let's say we go through the point 0, 1. And again, I'm going to plot that point. And this is a very, very unique function. If you take a look to the right of 0, 1, it falls on that asymptotic behavior and it looks like it's just going straight up. And to the left, again, it's on that asymptotic behavior and it's going straight down. So this is the only solution on my curve here, or on my slope field, that's linear. And that's a very, very unique fact there. Alright, let's go ahead and throw one last one up here. Let's say negative 1, 1. And again, I'm going to start by plotting that point. Looks about there. If I follow the flow of traffic or the breadcrumbs here, it looks like this is going up towards the end. And if I come to the left, I would say it looks like it's going down, maybe curving a little in there. Oops, that's a little sloppy. Just a little curve there. But again, it is not linear. I just want to be clear. These are clearly going up. And we've got, again, one particular solution to this differential equation. So remember, there is an infinite amount. This is just particular to this point. All right, well, let's try another example here. So this should be example 2 in your notebook there. And let's say the AP gave us the point 0, 1, and they wanted you to sketch a particular solution. So pause it, try it on your own, and see if yours compares to mine. So I've plotted my point 0, 1, and to the right it looks like I'm going to go up and then shoot upwards. And then you'll notice like it still looks semi-flat here, so I'm going to flatten off for a second and then shoot downwards. And again, notice I'm taking full advantage of that graph paper. I'm going from end to end. Okay, well let's try one more point. Let's go ahead and do the same thing. Go ahead and graph a particular solution at the point 1, 0. So again, pause it, try it on your own, and see if ours match up. So I've plotted my point 1, 0, and again, it looks like these are just shooting up to the right. And then to the left, notice it is flat here. It is a 0 slope right there. So just make sure yours looks flat there, and then shoots down. Now the AP is not going to go crazy on you. There's nothing that's going to be too insane. Things they are going to look for, of course, is that if there's a 0 slope, it looks like you're horizontal. Alright, so that's one thing to catch. And again, they're just going to make sure you go from end to end. Alright, so let's try another example. So this should be example 3 in your notebook there. And let's say we're given the point 4, negative 4. And we want to draw a particular solution through that point. So again, I would just plot that point and pause it, draw it on your own, see if our slope fields or our particular solution looks the same. So I would say that I'm very, very steep right here. Okay, and maybe less steep as I go up. See how it's a little less steep, so it should be curving out. And then very steep here. Okay. Let's go ahead and graph another one. Let's say right at 1, 0. So again, I'd start by plotting that point at 1, 0. And again, this is a very, very unique one. Notice it's on that asymptotic line. It's on this nice point here, and if I were to follow it to the right and left, it's creating a nice straight line. So this is that rare case, or the very unique case, where we have just a linear solution in here. And notice that will be the only linear solution. And let's go ahead and graph 2, 2 as well. We'll graph a particular solution through the point 2, 2. Now notice right at 2, 2 I have that flat line here, which means I have a 0 slope. So it's got to look flat there. Now to the left of it, it looks like it's going up and it's getting steeper. So it kind of goes out and then it goes up nice and steep. And to the right, so I've got my flat line of a 0 here. I can't go through this. I just have to remember it's asymptotic. So I just have to kind of follow it up. And again, it shouldn't touch it, shouldn't go through it. It's asymptotic. Alright, this one's a little difficult. So again, let's start by plotting that point 0, 2. And you'll notice something special about 0, 2. You'll see that there's a horizontal line here. So again, that's telling me I have a 0 slope, which here is implying that I have a max. So to the left, I mean, it kind of looks like I followed it up and went like that. To the right, looks like this. Now, it'd be nice if there were a few more lines on here. I can't actually touch this curve, and that's a huge deal. Do you know anything about this slope here? Okay, there are no tick marks. I don't know what the slope's doing. So all I can say is that it looks like it's going to be asymptotic to that x-axis. Alright, I can't touch that x-axis at all. Sounds a little difficult. If there were more lines, it would be a little easier. here's a great looking graph of a slope field. And again, I just wanted to show you this one to really stress the idea of parallelism. That these functions, I mean, if you look over here, it looks like they're kind of intersecting each other, where they're all kind of meeting up. But I just want to be clear that they are not touching. These are all very unique solutions. None of them, like I said, are touching each other. So it looks like whether there's 20 here, and again, this should just be stressing that there's an infinite amount of solutions. I could draw another one here, and here, and here, and here, and down here. Okay, so there's an infinite amount, and again, they are parallel in the sense that they are never touching each other. We have this nice asymptote in here as well. All right, well, we finally made it to the exciting part. Up until now, I've given you slope fields, and now it's your turn to draw your own slope field. So this is a very common question on our free response, is to draw your own slope field. And I would say it's probably the easiest and the hardest question at the same time, and I think you'll see why. It's easy in the sense that the math is very, very simple, and it's hard in the sense that this is very time consuming. And you know, on that free response, you're rushing, because you've got your 15 minutes, and so it's easy to make a mistake because of your rushing. So, you know, at the same time, slow down, but work at a fast pace. All right, so roll up your sleeves and here we go. We're going to draw a slope field for this differential equation, dy dx equals negative x over y, over the interval negative 3 to 3 and negative 3 to 3. So basically this is describing the x values, this is describing the y values. So here's how I attack it. I'm going to make a huge table of values. And I'm going to split this corner, and I'm going to say this section is for my x's, and this section is for my y's. And they told me my x's go from negative 3 to 3, so I'll just carefully fill those in. My y's are going to do the same, negative 3. And here's what we do. We need to take every point. So if you count these up, this is 7 by 7, so that's 49 values I need to find. And I'm going to start by taking this x value here and putting it in the x in the equation. And I'm going to take this y value here, put it in the y in the equation. So basically I have x over y, so negative 3 over negative 3 is positive 1, but there's that negative in front, so that value should be negative 1. And I'm going to do the same thing for each point. I'm going to take the negative 3 again, divided by the y value of negative 2, so that's a positive 3 halves, and there's a negative in front, so negative 3 halves. Now I'm going to do it again. Negative 3 divided by negative 1 is 3, and that negative in front makes that negative 3. Negative 3 divided by 0, anything divided by 0 is undefined. Negative 3 over 1 makes that negative 3 with another negative is a positive 3. Negative 3 over 2 is negative 3 halves, but that other negative makes it a positive, and then hopefully a positive 1. So hopefully you can see what I mean by the time-consuming part and the easy part at the same time. Alright, then we just go and we do the same thing with the next row. We're going to start with negative 2 for the x value and negative 3 for the y value. So I'll do one more with you. So I'm going to get positive 2/3 with the negative in front makes it negative 2/3. That's going to be negative 2 over negative 2 is 1, so negative 1, and then negative 2. Anything over 0 does not exist. This should be a positive 2, positive 1, and positive 2/3. So I'm going to suggest you go ahead and hit the pause button, fill in the rest of the table on your own, and then we'll meet back and compare. Alright, so I think you'll compare. Like I said, it's time consuming, but not very difficult at the same time. And we do kind of have to get this down to about a 2-minute process at the most here. So typically, the creation of this slope field is about 2 to 3 points depending upon the question. So now that we've got our values made, we actually have to make the slope field itself. So you should have a paper I gave you, and we're going to stick it right on there. Okay, so here's how we want to attack this. I'm going to start with the point negative 3, 0. Okay, so if you look at your table, look at negative 3, 0, and x is negative 3, y is 0. I've got an undefined slope, and of course an undefined slope is a vertical line. So I'm just putting a nice little hash mark vertical, nice and small, just like that. And now I'm going to do this whole column first. Alright, so let's go ahead and look at negative 3, positive 1. So negative 3, positive 1 has a slope of 3. Now here's what you're going to be graded on, and I want you to write this down and get used to this phrase. Relative steepness. And basically, nobody's going to sit there with a ruler and kind of, find the correct angle of each of yours or the correct slope of each of your tick marks, but they do have to be relatively steep compared to the next. So here's what I mean. At 3, 1, I need a slope of 3. So I'm not just going to draw in a random line. I'm going to literally figure out what my slope of 3 is going to look like. So basically, when I say slope of 3, I'm thinking rise over run. And if I want to be 3, I'm going to rise 3 and run 1. So at this point here, I want you to count up 3, 1, 2, 3, and run 1. Would you agree it's kind of right where my R is here? And basically, you're going to aim for that when you draw your slope. So I would say that is going to be my slope of 3. I am aiming. If I were to aim, I would hit that dot. All right, so at 3, 2, I need a slope of 3/2. So again, at this point, I need to have a slope of 3/2, so I'm going to rise 3, run 2, and that's what I want to aim for. So rise 3, that's 1, 2, 3 would be up here, over 2 would be over here, and I'm aiming at that point when I draw this. Okay, so relative steepness means that your slope at 3 better be a heck of a lot steeper than your slope at 3/2. And if we keep going, oh my goodness, the dog is going crazy. At 3, 3, at 3, 3, or I'm sorry, negative 3, 3, our slope was 1. So again, I'm going to look for a slope. If I were to be at this point and I want a slope of 1, I'm going to rise, run, 1, run. Rise, 1, run, 1, and I'm going to aim at that point. So my slope should look like that. And again, that should be less steep than I am at 3/2. So you're going to be graded on relative steepness. Negative 3, negative 1, looking at your chart, should be a negative 3. So I better look negative, so I'm going to go down 3 over 1. So I'm going to aim at that purple dot. At negative 3, negative 2, I should be negative 3/2, so I'm going to go down 3 from here. 1, 2, 3, and over 2, so I'm going to kind of aim over here. And then negative 1. Okay, so relative steepness. They shouldn't look the same if they're different slopes. All right, let me do one more line with you, then you're on your own. So I'm going to start at negative 2, negative 3. I'm going to start down at this point here. I should have a slope of negative 2/3. Okay, so I'm going to go down 2 over 3, which would be way over there, and I'm going to aim that way. So I'm going to say negative 2/3. Negative 2 should be a slope of negative 1, so I'm going to aim, like I said, I'm going to aim at this dot here when I draw my line. And then I should have a slope of negative 2, so I'm going to aim over at negative 2 here. At negative 2, 0, I'm undefined, so I should be a vertical line. Negative 2, 1, I should have a slope of 2, positive 2, so I'm going to rise 2, run 1. I'm going to aim at that dot. Hopefully you can see I'm aiming there. Then I should have a slope of 1. And a slope of 2/3. All right, well, you're on your own. Do the same thing and fill in the rest of this grid here. So pause it and fill it in on your own. All right, well, hopefully yours turned out to look like mine. And again, this is a slope field. It's just a bunch of slopes you'll see to that differential equation that we have. And that relative steepness is what we're watching out for. Is your slope of 3 steeper than your slope of 1? And vice versa. So just be real careful with your slopes. And like I said, I know it's time consuming. We're just going to have to work on our pace, and it's day 1, so there's no pressure. And we'll get there. So you'll notice that hopefully you see the infinite amount of parallel solutions, and I think that is pretty neat looking. I think you'll see a bunch of circles depending upon where you drew this through. Okay, now in that center there, we had like a 0 over 0, which was indeterminate there, so nothing's going to go through there. But we did have, like I said, a bunch of circles for our general or particular solutions. Well, we're going to get a lot of practice in class tomorrow graphing these, so come ready to go, and we'll see you then. Have a great night.